After the required parameters have been configured, beam injection and acceleration can begin. To set up the injection and acceleration, one needs appropriate diagnostics tools. To measure the position of the center of gravity, beam position monitors or pickup electrodes are employed. Current transformers of various designs are used to measure the beam intensity and its dependence on time. To assess the beam profile, that is, the width and radius of the charged particle beam, profile monitors are used. A beam loss monitor is used for measuring the amount and position of beam losses. There are more complex systems consisting of several separate elements. For instance, a system for measuring the frequency of transverse oscillations, or the so-called Q meter. An element of stochastic cooling is also applied in the diagnostics of the momentum spread of particles. In the pictures, you can see some examples of various diagnostics instruments. A pickup station is a normal metal pipe cut horizontally and vertically along the shaft. It works like an ordinary capacitive sensor of charged particles. To measure the high-frequency structure of a beam, a fast current transformer is used. To measure the permanent beam current, regardless of whether it is bunched or coasting, a DC current transformer is employed. The profile monitor, mounted directly on the nucleotron ring, must not influence the motion of the charged particle beam. That is why we use ionization profile monitors, the operating principle of which is related to the fact that the circulating beam ionizes the molecules of residual gas. The generated ions or electrons may be accelerated and directed towards a special detection device. By the distribution of the residual gas ions, one can draw conclusions about the distribution of the primary beam particles. A beam loss monitor consists of compact neutron sensors, which are located along the entire circumference of the ring, and the signal of which is proportional to the quantity of ion losses at a given point of the accelerator. The signals from the diagnostics tools are directed to the control tower, and, for example, the DC current transformer delivers the results of its work as a time dependency of the magnetic field value and the current of the circulating beam. The beam loss monitor shows the magnetic field cycle and the loss intensity at different points of the ring related to the cycle. For the tuning of particle injection and particle extraction, profile monitors of another type are used. They are based on measuring a beam profile with the use of wire sensors. The transparency of such a detector may be close, but less than 100%. That is why it cannot be used on a circulating beam. However, it provides valuable information for a single crossing beam. Here, you can see the structure of a device, a photo of the device produced in Bulgaria for channel transportation along with the results of beam profile measurements before the beam injection into the nucleotron. The instrument used for the measurement of betatron oscillation frequencies consists of a whole system with an intricate setup rather than just one device. There is a master generator that applies the signal, which is enhanced by a special amplifier, to the beam. The powerful signal is applied to the electric impulse devices known as the kickers. They affect the beam, whereas the response signal of the beam is measured by pickup electrodes. Next, by processing the signal from the pickup electrodes, one can draw conclusions about the frequency of the betatron oscillations. Some of the technical parameters of the devices constituting a Q meter are shown on the screen. To some extent, the diagnostics systems may be attributed to a system of closed-orbit correction. The system of closed-orbit correction includes an orbit measuring system. It is an array of pickup electrodes which are more or less evenly spaced along the entire ring. The position of the beam is measured at the location of each of these detectors. In order to correct the orbit, that is, to give it some necessary properties, 42 correcting magnets are used. The control window of these magnets can be seen in this slide. By configuring the currents of these magnets, one can observe how the closed orbit reacts to the changes in its current. By alternating the supply currents in each of the correctors, one can measure the matrix of the orbit response from the impact of the correctors and, based on the analysis of this matrix, set the corrector currents to an optimal orbit position. To that end, the beam needs to find its way into the accelerator. Therefore, an impulse injection is needed. A synchrotron is an accelerator with a constant orbit radius. A continuous beam cannot be placed on such an orbit. That is why one uses an electric impulse deflector in impulse injection. It switches on when the beam from the linear accelerator is transferred to the entrance of the nucleotron. After the whole circumference of the orbit is filled up, this deflecting element switches off. A magnetic septum is used to transport the injected beam as close as possible to the orbit. At the nucleotron, this magnet is called the inflector magnet. It determines the vertical position of the beam while it is injected into the vacuum chamber. By altering the voltage in the inflector plates, one can ensure an injection from different angles. By combining the parameters of these two instruments, an optimal beam injection into the accelerator may be secured. It is the first system we encountered, the impulse system, and it requires synchronization with the work of the remaining accelerator elements. Field detectors are used for the synchronization of the injection system. The injection system activates at a strictly predefined magnetic field value, which corresponds to the energy of the injected particles. After a beam is injected into an accelerator, it needs to be accelerated. This is performed by the radio frequency accelerating system. To explain its operating principle, I will have to back up a little bit, back to the phase stability principle. For a synchrotron, the phase stability principle is formulated in the following way. Two conditions have to be satisfied. The first one is the resonant condition. What are the challenges involved in fulfilling this condition? The particle velocity increases during the acceleration process. The period of its revolution changes, and at any given moment, the frequency of the accelerating field has to correspond to the particle revolution period. A mathematical formulation of this correspondence will be provided on the next screen. The second condition is applied to the amplitude of the accelerating field. The amplitude of the accelerating field has to be sufficiently large to ensure a corresponding increase in the beam energy. If these two conditions, the resonant condition and the amplitude condition, are satisfied, then the injected beam is automatically divided by the sequence of bunches, following with the frequency of the radio frequency field and steadily gaining energy. This is the phase stability principle. When we fulfill these two conditions, Vladimir Wechsler's phase stability principle takes care of the rest. How are the resonant conditions mathematically formulated? Perhaps I would like to dwell on that, but it is not that simple. The revolution period is the circumference divided by velocity. The frequency of the accelerating field should be equal to an integer divided by the period of particle revolution. H is an integer, which is called the harmonic number of the accelerating field. To consider the frequency of the radio frequency field, we need to relate the particle velocity to the value of the magnetic field. Let's take the same equation for the relation of particle impulse momentum with the magnetic field value and write it down through the given particle velocity, through beta. Having expressed the beta through the magnetic field, we obtain a three-story formula for the frequency of the radio frequency field. Furthermore, the accuracy of the correspondence of the magnetic field and frequency, a relative error, must not, in some cases, exceed 10 to the power of -6.